On Monday, January 15, 1990, at precisely 2:25 p.m. Eastern Standard Time, the nerve center of American communications began to bleed red. Inside AT&T's state-of-the-art Network Operations Center in Bedminster, New Jersey, automated telemetry monitoring systems suddenly lit up with a wave of critical alarms. On the wall-sized digital map of North America, a display designed to visually track tens of millions of telephone connections in real time, green diagnostic routing lines were abruptly replaced by a chaos of flashing red warnings. Within seconds, the signals indicated that 4 ESS digital electronic switching systems across the country were dropping off the grid simultaneously. At first, network supervisors assumed it was a localized hardware failure or a cut fiber optic trunk line somewhere along the East Coast. But as the minutes ticked by, the red tide didn't stop. It began cascading from New York to Atlanta, from Chicago to St. Louis, and across to Los Angeles. Every single second, thousands of long-distance telephone calls were instantly severed mid-conversation. 70 million phone calls vanished over a 9-hour period. Approximately 60,000 customers lost complete phone service. Wall Street brokerage houses, processing billions of dollars in equities, were rendered completely mute. Financial trading desks stood paralyzed. At major international airports across the eastern seaboard, air traffic control towers lost their dedicated long-distance coordination circuits, forcing ground stops and delaying over 500 flights, stranding 85,000 passengers on tarmac taxis and terminal gates. Emergency 911 dispatch centers found their secondary transfer lines dead. Hotel reservation chains, national credit card processing clearinghouses, and government agencies were instantly cut off from the outside world. It was the single largest network failure in telecommunications history. In 1990, AT&T carried over 70% of all long-distance traffic in the United States. Their network wasn't just a business infrastructure, it was considered the gold standard of global engineering, a system built with triple redundancy, automated failsafes, and an operational uptime standard of 99.99%. In the initial hours of the blackout, panic spread to the highest levels of the United States government. Intelligence agencies and Pentagon officials quietly convened to investigate whether the nationwide disruption was the opening salvo of a coordinated cyber warfare attack by a foreign adversary or a sophisticated physical sabotage of America's critical infrastructure. The truth, however, was far more disturbing. There were no covert operatives, no severed cables, and no malicious viruses. The force that brought the world's most powerful nation to its knees was a single, silent defect lurking deep inside a routine software update, a defect contained within one line of code written in C. To understand how a single error could trigger a nationwide collapse, one must first understand the sheer scale and complexity of AT&T's long-distance architecture. At the heart of the network sat the 4 ESS, the fourth number electronic switching system. Manufactured by Western Electric, these giant mainframe systems were engineering marvels of the digital telecommunications age. A single 4 ESS switch could process up to 700,000 calls per hour, dynamically routing audio signals through high-speed digital trunks using complex computer logic. Nationwide, AT&T operated a backbone network consisting of 114 of these 4 ESS switches, located in key metropolitan nodes. To manage call setups between these 114 switches, AT&T utilized an advanced protocol stack known as Signaling System 7, or SS7. SS7 operated as an out-of-band signaling network. This meant that control messages, such as verifying if a destination line was busy, routing call setups, or reporting hardware errors, traveled on a dedicated digital data highway completely separate from the actual voice channels. This design allowed calls to connect in a fraction of a second. If Switch A in New York needed to route a call to Switch B in Chicago, it sent a tiny SS7 packet ahead of time. If Switch B was congested or offline, Switch A would instantly reroute the call through Switch C in Pittsburgh. The entire network was engineered to be self-healing. If a 4 ESS switch encountered an internal memory corruption or a transient hardware glitch, its operating system was designed to execute an automated reset. During a reset, which took roughly 4 to 5 seconds, the switch would drop out of service, clear its temporary memory buffers, reinitialize its internal state, and rejoin the network. While that single switch was resetting, SS7 would automatically notify all neighboring switches to route call traffic around the disabled node. Once the switch completed its reboot cycle, it would send out an in-service status message signal. Upon receiving this signal, neighboring switches would resume sending call traffic to it as normal. It was a system designed to survive hardware failures, lightning strikes, and central office power outages without human intervention. Except in mid-December 1989, AT&T pushed a new software update across all 114 switches. The software update was intended to improve error recovery speed in the SS7 communication handling module. The switch software was written in C, the dominant system programming language of the era, known for its high efficiency, close to hardware execution speed, and direct memory manipulation. At the center of C's control flow structure is the switch statement, a mechanism used to evaluate a variable and execute specific blocks of code based on matching conditions, or cases. Inside the SS7 message processing loop, the 4ESS code monitored an incoming ring buffer containing status messages from neighboring nodes. To handle special error conditions, developers wrote a conditional if check inside one of the main case branches of the switch statement. Here is where the fatal syntax oversight occurred. In the C programming language, the break keyword serves a very specific structural purpose. When placed inside a switch statement, a break command instructs the computer to immediately stop executing the current case block and jump out of the entire switch construct. However, when an if statement is nested inside a switch statement, the rules of C dictate that a break command does not break out of the if clause. It breaks out of the outer switch block entirely. The developer who wrote the update intended for the break statement to exit an inner conditional error check, but because of how C syntax rules evaluate control structures, the break statement forced the entire SS7 message processing loop to terminate prematurely. When a specific, rare combination of conditions occurred, specifically when a switch received an in-service message from a newly rebooted neighbor while simultaneously processing an incoming data packet in its side buffer, the program hit the misplaced break. It bypassed the pointer cleanup logic that was supposed to clear temporary memory references. Instead of registering the neighbor as fully online, the switch inadvertently overwrote its own active memory pointers, corrupting its runtime data structures. Detecting internal memory corruption, the switch's built-in safety monitor instantly triggered a full system fault, forcing the switch to shut itself down and execute an emergency reboot. The bug was a classic race condition, requiring a millisecond-level collision of events to trigger, and because it only occurred during an extremely specific sequence of recovery messaging, it slipped through months of rigorous simulated testing, code reviews, and quality assurance protocols unnoticed. On January 15, 1990, at 2:25 p.m., that precise millisecond collision finally occurred in a single switch in New York City. What happened next was a terrifying demonstration of how high-speed automation can turn a redundant system into a self-destructing cascade. When the primary 4ESS switch in New York City suffered a minor transient anomaly, it initiated a standard 4-second reset. As designed, its neighboring switches detected the drop, rerouted active calls around New York, and waited. 4 seconds later, the New York switch successfully finished rebooting. It reinitialized its operating system and broadcast a standard SS7 in-service message to its neighboring switches, informing them that it was ready to process traffic once again. In Washington, D.C., a neighboring 4ESS switch received New York's in-service message. At that exact millisecond, the Washington switch was in the middle of clearing a temporary data buffer from a dropped call. The precise timing condition was met. The Washington switch executed the flawed code update, hit the misplaced break statement, corrupted its own memory pointers, and instantly crashed. Now Washington, D.C. was offline. Neighboring switches in Atlanta and Pittsburgh detected Washington's drop, rerouted traffic, and waited. 4 seconds later, Washington finished rebooting and broadcast its own in-service status signal. The switches in Atlanta and Pittsburgh received the message while processing active call traffic. They both hit the bug, corrupted their memory, and crashed simultaneously. The network had entered a self-sustaining feedback loop. Every time a switch crashed and successfully rebooted, its "I am back online" signal acted as a digital warhead, instantly triggering a crash in whichever neighboring switch received the message first. As calls were repeatedly rerouted to surviving switches, those switches became overloaded with message traffic, increasing the statistical probability that they would receive an in-service signal at the exact millisecond required to trigger the bug. Within minutes, 114 primary switches across the United States were trapped in a continuous, synchronized loop of crashing, rebooting, sending recovery signals, and crashing their neighbors. For 9 agonizing hours, engineers at AT&T's Bedminster NOC watched helplessly as the automated system tore itself apart at computer speed. Human operators were entirely powerless to stop the cascade manually, because the switches were failing and restarting in intervals of milliseconds, far faster than any human operator could diagnose or intervene. It wasn't until late that evening, after engineers systematically reduced network load by manually throttling long-distance call entries, that the frequency of SS7 status collisions dropped below the threshold required to trigger the race condition. The switches stabilized one by one, and by 11:30 p.m., national long-distance service was finally restored. In the weeks following the catastrophe, AT&T software engineers conducted an exhaustive line-by-line audit of the entire 4ESS code repository. When they finally isolated the bug, they discovered that the entire 9-hour national blackout, which cost AT&T over $60 million in direct lost revenue, and hundreds of millions more in downstream economic damage, came down to a single misplaced break keyword inside a nested conditional statement. They rolled back the software patch, replacing it with a corrected version containing defensive error handling and explicit control flow structures. The 1990 AT&T network collapse remains a watershed case study in computer science and system architecture history. It exposed a fundamental vulnerability of the modern digital age, the paradox of homogeneity. By deploying the exact same tested software update to every node across a nation simultaneously, AT&T eliminated software diversity. In doing so, they ensured that a single flaw would not remain an isolated incident, but an existential threat to the entire ecosystem. It proved that when code operates at scale, rarity is not immunity. A bug that has a 1 in a billion chance of occurring will happen every single day when your system executes billions of operations per second. In complex, tightly coupled systems, elegance and speed must never supersede defensive isolation and fail-safe boundaries, because as millions of silent telephone lines proved on a cold January afternoon in 1990, the difference between national infrastructure and catastrophic collapse can be as small as a single line of code. If you enjoyed this deep dive into the history of technology and system design, hit the like button, subscribe, and explore our full archive of software disaster documentaries on Silicon Archives.